Hello, and welcome to Lecture 4 on Chapter 3. For the beginning of this lecture, I would like you to go to Moodle, and in the folder titled Chapter 3, Biology and Behavior Lecture Videos, please watch the video titled Epigenetics. Welcome back. So I'm going to touch on this video as I go through this entire lecture. So we'll come and go from the video. So in utero, brain structures begin to connect because chemicals tell the brain what to do. There are chemicals that tell individual neurons, okay, you're part of the limbic system, you're part of the cerebral cortex, you go to the occipital lobe, you go to the thalamus. Major connections in the brain are governed by chemical influences. So we talk about this nature-nurture question. And when we're talking about the nature question, often, we're thinking about DNA, but we also need to recognize that we are chemical and electrical beings. And a lot of early development is chemical. Detailed changes in the brain, however, are governed by environmental stimulation. And there's a bit of, there's a concept of reciprocal determinism, which is kind of you bring yourself into the environment, and the environment shapes you, and then you bring yourself to the environment, and this give and take. I think of neurodevelopment in that way. That, so we're conceived, and, once we pop into the world, we have our whole brain. We have all of the structures. The structures are all connected like they need to be. They're going to continue to connect over time. But at birth, now we have the environment to factor into our development. And so we bring ourselves into the environment. We select our own environment. Our environment shapes us, and then we go into the environment and shape it, and then it shapes us. The concept of epigenetics works that way. Who we are, our DNA at birth is not what your DNA is right now in your life. It's changed quite a bit, and it will continue changing based on the environments that you put yourselves in. So, environmental experiences, especially during critical periods, or what we now call sensitive periods, are necessary for cells to develop properly and for them to make more detailed connections. So when we talked about attachment in Chapter 9, we talked about sensitive periods. So sensitive period is a relatively fixed period in time in which specific experiences must occur for normal development. So, attachment is one of the best examples I have of sensitive periods. Another is language development in children. One of the big jobs during infancy is to learn language. By the age of 3, most infants are fairly fluent in their native language. They found that you have about a 7-year window where the brain is just a language sponge. Children understand much more than they can say. And a lot of that just has to do with physical limitations of the vocal system. That, they just have to get bigger in order to be able to say what they actually know. But, with the sensitive period, you've got a relatively fixed period of time in which certain experiences must occur. For children with language, it's the first 7 years. Those first 3 years are critical. What's interesting is it's the first 3 years with attachment as well. Those early 3 years of life are really critical for many, many aspects of the human condition. Neuroplasticity is the brain's amazing ability to change, grow, and repair itself throughout the lifespan. Anytime the brain is changing, it's undergoing what's called neuroplasticity. the brain is not a static organ. It's quite dynamic, and as long as you're presenting challenges to it, it will continue to grow. It will continue to wire itself more and more and more. It'll grow even more intricate connections between neural pathways. Neural pathway is just a group of neurons that have wired together for a specific task. Now, neuroplasticity is what allows our brain to grow new connections, to become more complexly organized, and to repair itself when it's damaged. Neuroplasticity is strongest when we're young. As we age, our brains become less plastic. They're less malleable. And as we age, it's more difficult for the brain to repair itself when injured. I think neuroplasticity goes hand in hand with epigenetics. It's the same concept that, you're born with this brain. It is what it is. And then once you face environmental challenges, that triggers new wiring in the brain. It actually grows your brain. It helps rewire your brain. While plasticity decreases with age, the brain does retain the ability to rewire itself throughout the lifespan. I'm really proud of my mom. She's learning how to play the baritone ukulele at 75. And it's a challenge for her. And I told her, I'm so glad you're doing this. You're saving your brain. This is really good for your brain. And it is. Her brain is rewiring itself every time she has a lesson. And I just think that's pretty amazing. That it just takes doing something that you enjoy. And that 1 hour lesson has just helped your brain rewire. I think that's pretty dynamic. Now this brings us to neurogenesis. And this is the generation or creation of new neurons in the brain. I touched on this when I talked about the amygdala. And we looked at the taxi drivers, London taxi drivers. So we do know that neurogenesis happens. That the brain can create new neurons. Our understanding of it is very limited, though. There are so many questions, like, do certain people grow new neurons better than others? Are there certain environmental events that must happen to really capture neurogenesis, to really make it a dynamic process? When, at what age are we most likely to grow new cells? And neurogenesis was first discovered in the hippocampus, but we know it goes on throughout the brain. Recent research, however, is showing that neurogenesis is not likely in adults. This doesn't mean it doesn't happen in adulthood. What it means is that it's most likely earlier in life. But again, we're still in the infancy of researching neurogenesis. The textbook does need to catch up a little bit on this controversy, though. Some of the newer research is showing that neurogenesis is very limited in adulthood, if it happens in adulthood. It's certainly not happening in all adults. And neurogenesis and neuroplasticity are linked. So with neuroplasticity, enriched environments stimulate the brain to create new and more complex neural pathways. Neurogenesis, enriched environments stimulate the brain to create new neurons. So both neurogenesis and neuroplasticity work together to change the brain. So an enriched environment is any environment that creates challenges. So, often when parents have their first baby, They want to buy all the smart toys. They want to make sure their child is as smart as possible. And all these books say, buy this, buy this, buy this, buy this. And actually, that's not necessary. Enriched environments are necessary for children to grow their brain. But an enriched environment is simply any environment with challenges. An infant and toddler just needs to be able to explore and solve just basic problems that they encounter with everyday objects. And that's an enriched environment. For you and I, an enriched environment is, when we're having really interesting conversations or reading something that's really stimulating to our creativity, engaging in hobbies, things like that. Changes in the strength of connections between neurons underlies learning. Every time you learn something new, you change neural pathways. You're making individual neural pathways stronger. You might even be building brand new neural pathways. So for my mom, now that she's been learning the baritone ukulele for a while, she's grown new neural pathways because playing has brought challenges to her that nothing else in her life has, because it's a unique experience for her. And so this is actually changing her brain. There's the concept called fire together, wire together. The more frequently neurons fire together, the more connected they become and stronger that connection becomes. Basically, the more you use those cells, the more connected they become and the stronger that connection. Now, the brain does housekeeping. We have several periods in childhood and adolescence where the brain goes through and just kills off neurons or brain cells that it's not using. And that's actually a really good thing. You would think that killing off neurons would be a bad thing, but when it comes to pruning episodes, it's a really good idea, because why spend energy feeding those new neurons and oxygenating those neurons? If you're not using them enough, they're actually wasting energy. So the brain does some housekeeping. We know that male and female brains are different and similar. Men have a larger brain than female brains, only because their heads are bigger. They just have more room in their skull for their brain to arrange itself. So their brain looks bigger. But it's not, size doesn't matter, my dears. Female brains have a greater proportion of gray matter. Male brains have a greater proportion of white matter. So white matter are neural pathways of myelinated axons that connects to gray matter. I know, you're like, oh my God, what the hell? Okay. White matter is part of a neural pathway. And that neural pathway connects gray matter together. Females have more gray matter, which is actual cells and connections between cells, where men have more white matter, which is individual parts of those neurons, a specific type of part of that neuron. Basically, big picture, for some reason, men have more white matter and women have more gray matter. Now, women have superior language abilities. I talked about how for women, language is both a right and left hemisphere process, where for men, it's just a left hemisphere process. And this might be because the corpus callosum, women have a denser corpus callosum. And we talked about the corpus callosum in our previous lecture, joins the two hemispheres. and women are better at multitasking. We'll pick up here.